I'll draw a picture of a manifold.
Yeah.
So.
Okay, great. So welcome to everyone. I'm very happy to introduce the speaker for this week. So Boris Hanin from the Department of Operational Research and Financial Engineering of Princeton University will give 5 lectures about the mathematics of deep learning and neural networks. So we are very happy. So Boris had his PhD in 2014 in Northwestern University under the supervision of Steve Zeldich, which is a geometer, so had several contributions to spectral geometry and then the geometry of random fields. And then around 2015, I would say, he moved slowly towards deep neural networks and the mathematics of learning and machine learning. So he had a very large production that touches many topics and establishes connections with random matrix theory, free probability, differential geometry, stochastic differential geometry, you name it. And, okay. So Boris will give his lectures on the Blackboard. We are filming them and putting them on YouTube. And here you can find a link to a website where I will put a PDF of the lecture notes that will evolve a bit during the weeks, maybe even afterwards, about what Boris is going to tell us. And then, okay, so Boris, I'm looking forward to listen to your story.
Okay. Okay, so first let me say thanks for the introduction and for the invitation, Giovanni. I came to Luxembourg probably 2018 last time, is that right? And so it's very nice to be back. And it's very nice to meet you all. Okay, some of you I've already kind of met, and others maybe I'll have a chance to talk to after. So let me just give one word of context. So my plan for these lectures is to make them as accessible as humanly possible. Okay, so I think of myself as a graduate student in the lectures I would have wanted to hear. So if something is really trivial and obvious, don't hold it against me too much. Okay, and in particular, my hope for these lectures, they're very informal. So ask questions and interrupt and all of this. Worst case scenario, I don't get to everything, but it's no big deal. Okay, so let me just say my plan for this first lecture is to kind of give a almost like proto-colloquium type talk. I want to say something about what a neural network is. I don't want to assume that everyone here already knows the subject, how neural networks are used, what are the questions people try to answer, draw some pictures, God forbid. You'll see my picture drawing skills are not great. But okay, we'll do our best. Okay, so here's my plan. Since this is a talk hosted by a math department, I have to start with a definition. That's what I was always taught as a graduate student. Okay, so I want to tell you what the simplest kind of neural network is. So these are called fully connected neural networks. And okay, at a high level, whether a neural network is fully connected or not, it's just a parameterized family of functions. Okay, so I have to tell you what kind of parameterized family it is. So here it goes. So the inputs to my neural network are going to be called little x, and they're going to live in an n0 dimensional space. So n0 is my input dimension. That's what I usually call it. And I'm going to go from the input dimension to some output dimension through a series of layers. That's what they're called. And so the first layer looks like this. It's simply an affine transformation of x. So you have the pre-activations, as they're called, in the first layer at x. This is just an affine transform. You have a weight matrix W applied to x. You have an offset vector B. And this lives in Rn1. Okay, so this is the input dimension. Then you go to the first hidden layer width, as it's called. And we're going to do this a bunch of times. But when you do the second one and onwards, you apply a nonlinearity. So let me write it and explain it. So W2 looks like you get it from, Z2, you get it from Z1, just like you got Z1 from X. But you first apply a nonlinearity to Z1. So sigma is a nonlinear function, which you apply component-wise to Z1 of X. Then you add another bias vector, and here I am in Rn2. Okay, so these are matrices, these are vectors, and again, this is a function that is a function from R to R. And you just apply it component-wise to the elements of this vector. Okay, that's the definition. So you do this capital L times, capital L for number of layers. That's the depth of the network. And the output of the network, I write it Z capital L plus 1 of X, is just a kind of linear readout from the final hidden layers, it's called. Okay, so I'm going to carefully write everything out. It looks like this, just to keep the notation uniform. And this is an Rn L plus 1. Okay, so whatever I have done, I haven't completely cheated you. Okay, many of the things I say will be white lies. I'm not going to give full proofs of everything because it's only a bounded amount of time. But this is a parameterized family of functions. It goes from Rn0 to Rnl plus 1. And the parameters that parameterize it are the entries of these weight matrices W. These are called the weights of the network. And the components of these vectors B, called the biases of the network. Okay, if you were to fix all the w's and b's, you get a particular element of this family. But as you vary them, you get many different functions from Rn0 to Rnl+1. Okay, so let me just say that the NLs are usually called the widths of the network. So this is the width of the elf layer. And capital L is the depth, is the number of layers. And together, these are usually referred to as the architecture of the network. Okay, so once you specify the architecture of the network and your nonlinear function, you have some fixed family of functions from Rn0 to Rnl+1. Okay, that's my definition, and it may mean nothing to any of you if you haven't seen neural networks before, but I promise I'm going to try to land the airplane and explain a little bit about how they're used and why one ought to care and so on. But let me just stop and ask if this is clear. Okay, if this is not clear, it's going to be an utter disaster from here on out, so you may as well. Okay. Yes?
When you first learned the second layer, you were also about this sigma. What is that?
Yeah, so sigma is called the nonlinearity. Let me put it down here. So sigma is a function from R to R that you have to specify. It's part of the data of the definition. And it's called the nonlinearity of the network. Sometimes it's called the activation function as well. Okay, so I'm about to do two examples of neural networks that will hopefully make it more clear. But yeah, you have to give me these things, and then you get a neural network. Okay, great. All good? Okay, easy money. I used to have a roommate that would say everything was easy money because he got 100% on every exam he ever took. Okay, it wasn't fair. It wasn't fair. Okay, so let me do some examples. All right, so I want to show you two. So first I'm going to show you my favorite function computed by a neural network. You might think it's weird to have a favorite function, but okay, I'm a mathematician. I'm allowed to be a little strange. And then I'll show you my favorite class of functions computed by a neural network. Okay, so for this first example, I'm going to take the most popular nonlinearity used in practice, called the ReLU, the rectified linear unit, which is just the maximum of 0 and the input. Okay, ReLU is obviously a contraction invented by engineers, I feel. Okay, and so in this model, what are we going to have? We're going to have one hidden layer, so capital L is going to be equal to 1. The input and output dimension are going to be 1, so it's going to be a function from R to R, and the hidden layer width is going to be 2. Okay, very good. So let me draw this function. I'm going to draw it in three different ways. So first I'm going to draw it as I kind of wrote the definition, and then I'll show you two other ways to present this function. So you start with x in R, and you map it to z1 of x, which is just 1, 1, comma x, plus 0 minus a half. Okay, that's valid at the very least. Okay, and then you get z2 of x is the vector 2, negative 4 times sigma applied to z1 of x. Okay, this is a two-dimensional vector, so I'm allowed to dot it with this thing to get a scalar output. Okay, and don't kill me. Okay, sometimes I put a sigma on the outside, and sometimes I don't. In this case, I'm going to put a sigma on the outside for reasons which will become clear in just a moment. Okay, this is some particular function you get. It's a function from R to R. And what I want to do is I want to say there's a simple way that I think is really nice that computer scientists like to write down these functions. Because as you can see, just by telling you the weights and biases, you've probably learned nothing. If I were to ask you what kind of function is this, some function that I wrote on the blackboard. Right? That's pretty much all you know. So here's a nice kind of pictorial way of thinking about it. So this is called the computational graph of the function. So each dot represents a scalar. So you have one dot in the input because x is a scalar. Then you have two dots in your first hidden layer. Okay, so this is supposed to be z1 of x, and you put the weights, the 1 and the 1, on the edges, and you put the biases 0 and minus a half on these neurons, as they're called. And each of these neurons takes its input and applies sigma to it, the nonlinearity. So this neuron computes the first component. It's 1 times x plus 0. And then you apply sigma to it. And this neuron computes 1 times x minus a half and applies sigma to it. Okay, and then you collect them back in the output. So this is the output. And you have 2, negative 4. And you have your bias, and you have your sigma. So this is sometimes called the computational graph of the neural network. It's a kind of convenient way of understanding what's going on. This is the input. This is the first hidden layer. Okay, this is the output. If you had more hidden layers, you would just add more layers this way. Kind of a beautiful thing. Okay, so let me call this the computational graph. Computational graph. Okay, but now, this still is probably not very helpful in the sense that if I still ask you now, what function is this? Okay, it's a little more clear what the architecture of the model is when you draw it this way for me. Yeah. So I didn't add a 0 here. I had 0 bias. So it's just I record these biases in this way. Yeah, thank you. Okay, so now let's graph this function. Let's actually do a real graph and see what this function is, and you'll know why it's my favorite function. Or at least you'll have a better sense of why it's my favorite function. Okay, so we can do this together, I hope. Okay, here are the real numbers. It's a function from R to R. Okay, so I claim there's going to be 3 interesting inputs. There's going to be 0, and a half, and 1. Okay, so maybe it's a good question for the graduate students, okay, just so that you're actually following along, okay, or maybe for anyone who wants to answer. So what happens when the input x is less than 0? So let me ask you, what's the output of this neuron? What's the output of this component? What's sigma of x? 0. Okay, very good. So this neuron is off, as it's called. ReLU neurons are either on or off, depending on whether you're outputting 0 or the input. What about this component? Sigma of x minus a half. It's even more negative, so it's still 0. Right? So the output is 0. You're just dotting with the 0 vector. Okay, very good. So over here you get a nice function which looks like this. I don't know if you can see this yellow. Hopefully you can. Okay, so now what happens between 0 and a half? So what does the top neuron do? So it just returns x, right? It's sigma of x, but x is positive. So this top branch kind of gives 2 times x. But this bottom branch, is it on or off? It's still off, right? Because this is x minus a half down here. So maybe it makes sense for me to say, this is, let me write it out explicitly, 2 sigma of x minus 4 sigma of x minus a half. Maybe that's a helpful way of writing it. Right, so this sigma is on, this sigma is off. And you get, because the output is positive, just 2 times x. So you get a function with slope 2. Okay, and I've done this before, so I've normalized it to go up to the value 1. Okay, now what happens between a half and 1? Well, this thing still computes in x, but now this thing turns on, right? X minus a half is now greater than or equal to 0. And so I get something with slope 2x, okay, minus 4x. So I get something with slope negative 2 all of a sudden. And so I go back down to this point. And then at this point, the input to this final sigma becomes negative. And so I get 0 again. Okay, so this is, at least sometimes in signal processing, called a hat function or triangle function or whatever you want. And it's like a basic building block of signal processing. Okay, it's some discrete version of go up to 1 and come back down. And the reason I like to draw this is that it gives you a hint for what these ReLU networks do. Right? So when this neuron turned from on to off, you got a change in the slope of your function. Suddenly you got a slope of 2 because it's 1 times 2 is 2. Then when this neuron turned from on to off, you got another change in the slope. And this time the change in the slope was 1 times negative 4. And so the slope became negative 2. And then when this neuron turned from on to off, you again got a change in the slope. Namely, you just got the constant function. Okay, so you can kind of see how very simple neural networks compute nonlinear functions, at least with ReLU. It's an almost combinatorial process. Some neurons are on, some neurons are off. And as they turn from on to off or off to on, depending on which way you think about it, the slope of the function you compute keeps changing. Okay, so when people actually use ReLU networks in practice, they're just doing some version of piecewise linear approximation to high-dimensional functions. That's ultimately all they do. And this is like, okay, the only example I can draw on the board and not make a complete fool of myself. Okay, or not make a complete fool of myself with probability 1. Let me put it that way, okay? Okay, so let me just pause for a moment and ask if what I wrote is kind of clear and sensible. Okay, questions or comments about that? I need some kind of feedback. Is it clear what I'm saying? Okay, excellent. Clear. That's what they tell all the speakers to get them off the stage, right? Okay. Move this down just a little bit so it's not quite as ugly. Excellent. All right, so let me do one more example, if you don't terribly mind. And then we can talk about how neural networks are used. So here's example number 2. All right, so this example is just going to essentially be a generalization of the first example. Okay, so here again, I want sigma to be ReLU, so same nonlinearity. I still want the depth to be 1, so only one hidden layer. I want the input and output dimension to be 1, same thing. But I'm going to take a general hidden layer width, n greater than or equal to 1, and 1. Okay, so instead of having a two-dimensional representation in my hidden layer, I'm going to have any representation that I like. Okay, and the computational graph for such a network looks like this. You start with x, and then you have n1 dots that you're going to add. These are the components of your hidden layer. And then you have 1 dot for the output, because I'm making it a scalar. And then you just have weights that parameterize kind of these edges coming in and out of the neurons and some biases. Right, so this is W11, this is W12, W1 and 1. This is W21, W2, excuse me, let me put it down here, W22, W2 and 1. And then there are biases, B11. I promise I won't write this every time. I just find it useful to see it once. Again, maybe I have a bias here, B2, which I will omit the subscript on. Okay, so that's what the computational graph looks like. And then a formula is just like this. Z2 of x is equal to this bias B2 plus the sum on I goes from 1 up to n1 of W2I sigma of W1I times x plus B1I. Okay, if you want it to be very explicit. Okay, so either way you prefer, this is what a one hidden layer network looks like. And okay, I'm just specifying that my sigma is the ReLU, because that's a simple case to consider. Okay, so what I want to do is I want to give you a very simple characterization of what these functions are that you can get. Okay, so here, unlike the previous case, I've left the parameters w and b unspecified. They can be whatever you want. So now you have a collection of functions. And the question is, what collection of functions do you get? I claim it's something you've all seen before, but maybe you didn't know that you've seen it in this way. So I'm going to write it this way. Maybe you can help me fill in the blank. So every something, 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 something function, maybe I leave myself a little more room, has the form, okay, pound. I'll just give this some kind of name, just so I don't have to rewrite it. Okay, so what kind of functions do you think you get? Anyone have an idea? I'm doing well on time, so I'm not going to hurry. Okay, great. And then what's the role of n1? That's the only thing that's left. So you're totally right. They're always going to be continuous and piecewise linear, no doubt. Yeah, precisely. Okay, very good. So you can't full mark. You can try, but you can't do it. So indeed, so this is going to be the mark lemma. That's what I'm going to call it from now on. Okay, so every continuous and piecewise linear function with at most n1 minus 1, it turns out, breakpoints or places where the slope changes can be written in this form. Okay, and let me just give you a picture proof, just so that you see I'm not a total crackpot. So you know, every function of this form can be written like this, right? There are some breakpoints where the slopes change. I'm going to call them xi1, xi2, to xi n1 minus 1. And I'm going to have a funny normalization, which is that I'm going to call S0 my incoming slope, and I'm going to call S1 the slope between xi1 and xi2, and then I'm going to call S1 plus S2 the slope that goes out next. And then finally, I'm going to call this S1 plus dot 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 plus Sn1 minus 2, and this slope S1. So I'm basically just giving names to the increments of the slopes. Okay, you can write every continuous piecewise linear function with n1 minus 1 breakpoints in this way. And now the point is that this is just the graph of the following one-layer ReLU network. So if you just take, excuse me?
Sorry, is it n1 minus 1 or plus 1?
Oh, I started at 0. So I haven't. So I think I should have n1 minus 1 of these because there's S0 and then there's 1 coming out to the right of each one of them. Well, but I had a sigma in the final layer. That sigma gave me the extra one. Yeah, right. So, okay. Everything's a white lie, but not totally incorrect. Okay, so here's the way you write this down as a ReLU network. You do minus S0 times sigma of minus x plus psi1. So this function turns on to the left of psi1 and matches the incoming slope. Then you sum up over the other ones, n1 minus 1, and you do si times sigma of x minus psi I, and then you add the bias to fix the overall value. The point is that this function matches the incoming slope here, and then these ReLUs just increasingly change the slopes by the increments that I've indicated. Okay, and you fix this value of the bias by, for example, setting the value at psi1 or something like that. Okay, so this is a one-layer ReLU network. All the weights are either plus or minus 1 in the first layer, and the weights in the second layer are the increments in the slopes that I wanted to. Okay, so this is just to indicate that this is not a hard lemma. I just wanted to give some kind of example of what these things are, rather than kind of plowing ahead. Okay, so are there questions or comments about this? I'd like to kind of move on to the next part of the presentation where I tell you how neural networks are used and really what the big questions are. But I thought if you've never seen a neural network, it's good to see at least like 1 or 2 examples. Yeah?
Do you know what would be at least 3 or something? Like if you just have one sigma, say, then on one of the sides, the slope has to be 0.
Yeah, so that's why it's n1 minus 1. So if n1 were 1, then you can have 0 breakpoints. If you have 0 breakpoints, you're just a continuous function. But then to make more breakpoints, you need to add more sigmas. Does that kind of make sense? Yeah. Yeah.
You briefly mentioned higher dimension functions, but this is just for R, is that?
Yeah, so the short answer is it is interesting and tractable with one layer to describe the kinds of functions you get with ReLU networks. And I'm going to come back to them actually, well, in the last lecture. But you don't get all piecewise linear functions. There's way more partitions of the input space in higher dimensions. And so it's an interesting question which ones you get and which ones you can learn and so on. So, yeah. Yeah, please?
How the effect of adding more layers would be different than just adding width to some layer because then we just increase the number of points.
So okay, that's an excellent question, and I'm going to leave it for you as an exercise until the 5th lecture, in the sense that I claim there's a very big difference between adding neurons to the hidden layer and making more layers in terms of the number of breakpoints you can create. Okay, I'm going to leave it somewhat cryptically in that way, so I apologize. I'm going to be smart. I'm going to attempt to be smart. It's hard to be smart, but I'm going to start over here because I know where I'm going, believe it or not. Oh no, I lied. I didn't know where I was going because I left the eraser up here, I think. No? Anyone see the eraser? Oh, yes, you're right. Thank you. That's what I was looking for. Excellent. Very good. Okay. So let me tell you how neural networks are used in practice. I'll give you a kind of sketch of that. And the point is that most of the interesting mathematical questions, at least from my point of view, about how neural networks are used, come about by understanding why what's done in practice actually does anything sensible. Okay, so I can't really formulate the questions without telling you a bit of what people do in practice. Okay. Very good. So let me give you my abbreviated version of the typical use of a neural network. Okay, so typical use. So for me, a typical use has 5 steps. Okay, 5 is somewhat arbitrary, but that's how I think about it. Okay, so step number 1 is you get some data. So the practitioners will kill me for this, but for me, a data set is just a symbol. Just a bunch of inputs, xi, and a bunch of outputs, f of xi. And I will usually use little n to denote the number of training data points that you have. Okay, so the way you should think about this is that there's some function f, and you don't have a formula for f. In fact, you would like to learn a formula for f, but what you have are its values at some points. Okay, so here's a good example. If I take a picture of this room with my phone, maybe the x is the picture that I took, and f of x is the number of humans in the room. Okay, so it's something you can ask a human to, with high probability, correctly identify the number of humans in a room. Something our brains are good at doing, but it's hard to imagine a formula. Like, what do you do with the top left pixel if you're a computer? You know, so that's what I mean. There are lots of functions for which you can get good estimates for its values, but it's hard to know how to actually compute it on a computer. So our goal is going to be to find an approximation to this unknown function f. And for that, you have to fix an architecture. So fix an architecture. So in other words, I'm going to, just for the sake of this lecture, choose the nonlinearity and the hidden layer widths and the depth. Okay, this gives me some family of functions that you can imagine using. So in fact, I'm going to draw them in 2 ways. So over here, I'm going to draw the parameter space, as it's called. So the R number of parameters. So it's just the number of weights and biases in my model. Okay, and I typically call these things theta. So theta is just the vector of all the b's and w's that I have in my network here. And as I move theta around, I get different functions. But the whole point, and really in some sense the difficulty of the subject of studying neural networks, is that, okay, the space of functions you get is complicated. So to each theta, there corresponds some function z l plus 1 of dot with parameters theta. So when I want to emphasize that this is a parameterized family of functions, I typically put the input to the network here, and I put the value of the parameters in the second slot. Okay, so as you drag theta around over here, you get a very complicated way of parameterizing some high-dimensional space of functions here. And I draw it as a kind of manifold, partly to please the geometers, but really because the map from theta to z is highly nonlinear. Okay, that's kind of the whole difficulty of what's going on. Okay, so this is step number 2. And what you hope, but are not sure of, is that somewhere here, either the function f that you were trying to learn lives, or maybe some good approximation to f lives. Okay, so if you're a person that does approximation theory, there are many questions of the form, what kinds of architectures approximate what kinds of functions at what rate, and so on. Okay, that's like part of the connection to math. Okay, but we go on, because the way you actually try to search for f is as follows. So you first initialize the network, so initialization, which just means you choose theta at random. Okay, and I'll say much more about how to choose theta at random in the subsequent lectures, but from the point of view of the parameters themselves, i.e. the entries of these weight matrices and the components of these bias vectors, the probability distribution is very simple-minded. Just think IID Gaussian for all of them. Okay, so I'm going to draw it as a very simple probability distribution over here. Okay, I'm just kind of drawing some crazy picture. And so in other words, I'm going to think of this as being theta at time 0. This is before I've done any learning. So this is the randomly initialized neural network where the parameters are random. And so a lot of what I'll talk about is how to study random neural networks, by which I mean neural networks at the start of training. But because this map from theta to z is complicated, you get a complicated probability distribution here over the functions. And so really the goal is to describe what kind of probability distribution you get over here. Okay, so much more about that later. So you initialize, but of course, your random choice for z, l plus 1 at time 0, whatever, has nothing to do with the function f. You haven't used your data yet. Okay, it's pretty sad. So what are you going to do? Okay, you have to do optimization. Optimization. And in optimization, what you do is you seek to take this initial choice of theta, so I'll say theta of 0, and you improve it by making little steps to fit your data. Okay, so you improve theta by something like gradient descent or stochastic gradient descent or whatever. It doesn't matter so much what I'm about to say. It's some first order method. And it looks like this. Okay, so theta time t plus 1 is theta time t minus, you take a small step in the direction of the negative gradient of some objective function. And this objective function is always some empirical risk. So for example, maybe it's the average over the training data of the squared difference between what you're currently predicting and what you're supposed to predict. Okay, that's just an example. People use all kinds of losses. I call it L for loss. That's typically what people refer to it as. Okay, so in other words, what's supposed to be happening? Well, okay, it's hard to prove, but it's easy to draw. So this optimization procedure just says take little steps in parameter space until you hopefully have fit the data that you have. So, okay, who knows what it looks like over here? But what you hope is that over here, it looks kind of like this. You're moving around in function space. And, hopefully you end up at f. Okay, it's easy to draw the picture, right? It's just hard to prove that it happens. But it does happen in practice. That's why people use neural networks. Okay, so that's kind of step 4. And you might think that's it. But really, the money maker, so to speak, is in step 5. In step 4, you've just memorized the data that you have. So I call it maybe testing or inference. So when you test neural networks, what do? You get a new input, get a new x, and you check whether or not you make a good prediction. You check whether or not the predicted output, x, at theta star, which is what I'll call the final learned setting of your parameter vector, is it close to the f of x you were trying to predict? Okay, and if it is, then you've done a good job of approximating your function f. And if it isn't, you just got fired from your job. Okay, unless you're a mathematician, in which case you just don't report it to anyone and it's fine. Right? That's the truth of the matter. Okay, so somehow this is like my attempt in one board. That's why I wanted to fit it on one board to give like the most ridiculous crash course on what neural networks are. Okay, there's some parameterized family of functions, and you use them to fit data sets by some local method. Okay, you just search around the parameter space and you pray. That's pretty much how neural networks are used. Okay, so yeah.
Sorry. Is there also an option for the initialization, for the third step, to say, okay, I roughly believe in this type of model, so let me pre-estimate my senior.
Yes?
This type of
Yes.
and use that as initialization. In a way, I incorporate maybe my beliefs or
So the short answer is yes, and the long answer is no, which is kind of ironic, right? So the truth is this: people do all kinds of things in the real world. Well, like the first time you train a neural network, so presumably everyone has like used ChatGPT or heard of large language models or whatever. When you use a neural network, there's typically 2 steps, at least in the modern sort of formulation. One is you take a gigantic neural network, and you train it really according to essentially this kind of procedure from scratch, so to speak, from a random theta. But then in the second step, rather than throwing away all the work you did on one data set, you try to reuse the neural network you got, and you fine-tune it on a downstream data set. You do a little bit more optimization on the same kind of model you started with, but from the theta that you learned before. So people definitely do both. But okay, like I sort of advertised, almost everything I'm saying is kind of a white lie. There's lots of interesting and kind of complicated details for how people do each of these steps. But broadly, this is the procedure. Yeah.
So in step 1, you have your data as x and f of x. Now, the way I read it, the x's are non-stochastic, right? So what if instead of x's and f of x's, we have random x's and y's? So
yeah. So right.
What function would this algorithm and then approximate?
So okay, great question. And the short answer is, for sure in my mind, the x's are always random, and f of x is some true f of x plus noise. I never said it's a deterministic function. It's just in the real world, you just get some x's and values. You don't even know if you don't exactly understand the statistics by which they were sampled or whatever. But surely mathematically, it's very important and interesting to understand what happens when you integrate out the data generating process. And you ask what you would learn typically or on average or whatever. And so then everything from step 2 onwards becomes stochastic.
So if I function. What is the function of x that here? Is it the conditional expectation of y given x?
So, well, it depends on which loss you're going to use. What you're, if you're doing a classification problem, maybe it's going to be some kind of cross entropy type loss. If I'm doing regression, I'm just trying to estimate the conditional mean. It depends a bit. But in the end, all this formulation is covariant in the sense that I think of the data as random but kind of frozen, and then I run this process. And you can call them Fs or you can call them Ys. It doesn't matter from the point of view of this objective. But it's very important to ask what happens with high probability over draws of the data set. That's kind of your question, essentially. Yeah. So I'll say something about that. But OK, it's one of the big questions we really don't understand about neural networks. What happens when both the data set size and the neural network become large? How do you do kind of non-parametric statistics for this kind of learning procedure? And so if I have time, I'll say something about that in lectures 3 and 4. But I don't know if I'm, in fact, going to get to it. Yeah.
Maybe it's related. How do you make sure that the function f belongs to the set of possible functions, or at least it's close?
Yeah, so it's a great question. And OK, let me put it this way. The truth of the matter is the neural networks people use in practice are so big in the sense that the number of parameters is so incredibly massive. Like think billions or trillions of parameters, that for me at least, the space of functions that you get is virtually all possible functions. Now, okay, it's not literally true, obviously. But so you just, in practice, increase the number of parameters until you get more and more functions. One of the reasons I like this example is you can see kind of an example of the universal approximation theorem, right? If I have more and more neurons in my hidden layer, any function, any reasonable function, can be approximated by piecewise linear. So if I just throw more parameters at the problem, I can basically get any function I like, or approximate any function I like. But in general, you don't know. You don't even know what the true f was. That's the whole point. So you just hope.
So it's not just something that you need to understand from the structure of the problem that you have. Just
right.
architecture that works for everything.
So no. I definitely shouldn't say that. What I should say is, in the real world, certain kinds of data sets are empirically better to fit using certain kinds of architectures. Sort of transformers or convolutional neural networks or residual neural networks or graph neural networks or whatever. There's different architectures. I just presented the simplest one because I wanted to get somewhere rather than be stuck in a saddle point, so to speak. OK, so yes, there's some adaptation. But usually it's like inspired trial and error. I mean, if you ask me what are the statistics of natural language data, I'm not sure. You know what I mean? So I don't know what architecture to use as a result. Yeah. Good. Other questions or comments? OK, excellent. Please keep asking. OK, good. So I'm going to try not to erase this, but we'll see how it goes. Sometimes I get too excited and I erase things. OK, excellent. Don't need this after all. OK, so let me now switch to what are the big questions that people ask about neural networks? OK, so I told you what a neural network is. I told you how people use a neural network. And then you might be thinking, well, like I used to have a colleague, I won't say who it was, when we were discussing a Fields medalist. He said, excuse me, but where are the theorems? OK, so that gives you a sense of where he was from, but doesn't specify the person. OK, so what are like the questions before the theorems? What is it that one would like to actually prove? Or is it just an exercise in kind of doing something that's not obviously useful?
Sorry, to the last question, you do not know the function of f. How would you do the testing phase?
Yeah, so normally what you do is you take your training data and you split it in a testing and a validation set. So you just do sample splitting. That's the short answer in practice. Yeah, indeed. But you basically assume that you have access to many samples because you're going to test it later on. Like you make a self-driving car. I mean, in the end, you just have to deploy the thing and see how it does. It's a little scary, but that's how it is. OK, very good. OK, so let me talk about big questions. So I write it with capital Q for big question. OK, OK, I'm doing well on time, so I feel good. So let me go through what I think are a bunch of the questions that people have asked themselves about how neural networks work. So for me, when you look at steps 1 through 5, the more you think about it, the more insane it looks. I mean, I'm telling you, right, I have 100 billion dimensional space over which I'm doing optimization. 100 billion parameters, that's good. And I'm going to learn a function of, let's say, 10 million variables. Having 10 million pixels isn't so crazy in an image. And I'm telling you that I can do it and that it actually works well in the real world to some extent. Okay, all of that sounds too good to be true. And so that's one of the reasons I like these machine learning questions, is that they do work. And so there's something to be understood. And maybe the first thing to be understood is what I'll call the success of non-convex optimization. Convex optimization. So I was always taught, I kind of came up doing mathematical physics, took a little bit of statistics when I was growing up too, that once you're trying to optimize a non-convex function in many variables, you're pretty much screwed to leading order with high probability and so on, because, well, basically the way it was explained to me is people would draw this kind of picture and then they would walk away from the board, right? So they say, here's the theta space, here's the function L of theta. Okay, you're going to randomly initialize your function, you're going to do some kind of local search, you're going to find this local minimum, and you got fired from your job again. Okay, that's what people told me. It's literally that to rewrite the textbooks. But somehow, this is just not the right picture of what's happening. Okay, more seriously, if you've ever studied spin glasses or other kinds of difficult sampling problems, there are many interesting landscapes in high dimensions that have many, many non-optimal local minima. It's hard to search over them. But this doesn't happen with neural networks. So the way I would phrase it is the function you're minimizing, this function L, from this high dimensional space, R number of parameters, which, like I said, can easily be hundreds of millions or billions or whatever, to R, is non-convex. That's for sure true. Okay, but empirically, a local method, like gradient descent, like GD, finds a global min. Okay, and I'm just going to put question marks around it to indicate that this is an unusual situation. So the question is, what's going on? Obviously, if something happens, in fact, when you take your first class on neural networks, they will tell you to check that your neural network works, make sure that you can exactly fit all your training data. Okay, take a relatively small training data set, just make sure you can fit everything. So that's just how you know you implemented things correctly. Okay, so what I want to do is I basically want to offer what I think is one of the most important intuitions or heuristics for how to think about what neural networks are doing and why they're useful in practice, why optimization in this case is successful. And so here's kind of the key observation. At least, okay, this is my take on it. So neural networks in practice are over-parameterized. So let me tell you what that means. Parameterized. It's very long to write. But this means something very simple. It just means that the number of data points you're trying to fit is much smaller than the number of parameters in your model. Okay, and I'm going to try to give you a heuristic explanation for why this over-parameterization actually should explain why optimization was successful. Okay, so let me give this thing a name. I call it OP for over-parameterization, so I don't have to keep writing that. Okay, you can think of it this way, right? Every data point is like an equation. At a given input, you want a given output. And every parameter is like an unknown. So you have a situation where you have way more unknowns than equations, like an underdetermined system of equations. And so from this point of view, maybe it's not so surprising that it's easy to solve, right? So maybe I'll write it here. So kind of the first implication of this is that you expect infinitely many global minima of L. Global minima. Okay, so right, if you just do some very rough kind of algebra geometric thing, you expect that the dimension of the space of global minima of your loss function is like the difference between the number of parameters and the number of data points. And so when this difference can be whatever, 10 million, 100 million, something like that, you expect there to be very large high-dimensional manifolds in the theta space, in the parameter space of ways to fit the training data. So let me kind of dramatize this, because I think this is a useful picture. Okay, so here I am back in my kind of featureless parameter space. Parameters. And here I am at some value of theta. So the confusion in some sense, why the question, why people thought it would be hard, is that your function L is very complicated. So I'm just drawing the contour lines for L. It's non-convex. It can have lots of islands. This is what you think it looks like until you kind of realize that it probably doesn't. Okay, so when you have a function like this, yeah, it's unclear that a local method is going to find a global minimum. But here's the kind of key point, right? So your function, both in my example and usually in practice, the function you're trying to minimize, the loss, depends not only on the parameters, but it actually depends on the parameters through the values on your training data set. Okay, so there's a map that takes this high dimensional space from R number of parameters down to a lower dimensional space, which is R number of data points. So this is R number of data. And I will denote the map like this. It's just the value of your model on your training data set. So it's just the values you get at the current theta on your examples xi that you had. Okay, and you agree that at least the loss that I wrote down factors through this map. It only depends on the parameters through the outputs of the network. And over here, the map is very simple. The function is very simple you're trying to minimize. Its contour lines in the example I gave you are just convex, right? It's a convex function of the outputs of the neural network. It just wasn't convex in the inputs. Okay, so where in the heck am I going with this? So here's the key point. Okay, at least if you're, let's say, a physicist, or you're doing something on the back of an envelope, if you have a map from a high dimensional space to a low dimensional space, and it's not very poorly constructed, what you expect is that the Jacobian of this map is full rank. It's a submersion. Okay, so you expect, this is where the heuristic comes in, that the Jacobian with respect to theta of this map ZD is full rank. Okay, since I'm just giving you a heuristic, I'll just say for every theta. That's not literally going to be true, but don't mind me. Okay, so now let me explain, once you buy this statement, that the Jacobian of this map is full rank, let me explain very simply why optimization is always going to succeed. Okay, so what do you expect from a local method like gradient descent? Well, you expect to come to a local minimum, or like a stationary point of the loss. Okay, so imagine you're at some stationary point. So imagine that the gradient with respect to theta of your loss at theta is equal to 0. This is the, oops, too many thetas. This is the theta that you found. Well, the first thing I said is that you can use the chain rule. The loss depends on theta only through ZD of theta. Okay, so this is the same thing as saying that the Jacobian with respect to theta of ZD times the gradient with respect to Z of L at ZD equals 0. Right? That's the correctly written chain rule, I hope. Okay, but the whole point is if you believe this Jacobian is full rank, then this is the same thing as just asking that the derivative of the loss with respect to the outputs is 0. But as a function of the outputs, your loss is convex, or it's whatever nice function you want it to be. And so this can only happen, there's just one global minimum for the loss, right there, where you fit all the training data points. So this means that ZL plus 1 of xi and theta is equal to f of xi for all I. Okay, that's my pseudo proof. Okay, don't take it too seriously. That optimization is easy in high dimensions. That's what neural networks teach us. Optimization in high dimensions is very easy if you have way more parameters than data points. Yeah, please.
There's come on, say that the function has too many parameters, then you're fitting the data, you're fitting your modeling the noise.
Well, no, we're coming to that. So indeed, okay, very good. We're coming to that. For now, I'm just saying, forget about generalization, forget about testing on new data points. I'm just saying, like, confusion number one or mystery number one is, why do you actually fit the data? Like, why does your optimization procedure converge and give you a global minimum? And I'm saying there's a simple reason for that. But you've preempted me for the second kind of question. So indeed, okay, if you believe me that optimization is supposed to be easy, you're paying a big price. Right? Now there's infinitely many ways to fit your training data. And some of them will be crazy. They're just going to oscillate up and down, up and down. And the question is, like, how do you find good ways to fit the data? And why do neural networks do that? So that's going to be question number 2. Okay, so I'm going to write that in a second. But I just want to see if there are other comments or questions about this. Okay, excellent.
And why don't you
So if you took sigma as linear, you could only learn linear functions of x. No, but no one said your data generating process is linear. Like if I want to classify the number of humans in this room from a picture, right, a logistic regression model won't do very well. And so you somehow, the nonlinear sigma lets you parameterize all functions. And still somehow the optimization is fine. That's kind of what I'm saying. Yeah, I mean, it's a reasonable question, but that's kind of the only answer I can think of. Yes, please.
It's a comment on what Monica said, but like if your sigma is linear, then your picture that you just draw, then you end up in a hyperspace, like a strict hyperspace.
Yes, that's right. So in fact, I'm going to draw that picture in a second. That's going to be quite relevant. Right. Indeed. Totally agree. Yes, please.
I'm going to repeat probably the same question, but for parameters, it's a little subtle, right? You're not thinking really on parameters. There's something different because what Ivan is saying indeed has like many parameters, but in this case, if everything becomes linear eventually, it's gonna, a bunch of parameters that you fit in, they are transforming it to the...
So I disagree with you. So it's more complicated than you think, but you're thinking in the right direction. So okay, let me just say that's going to be the next mystery. Okay, so let me do it. The crowd seems to be going wild for, So I do it. Okay, so I'm going to erase this, assuming everyone's okay with that, because I want to keep that up. That's why I wanted to ask for questions on this thing first. Okay, very good. So. Good. Very good. But so I think this gets to the point of what I was saying. There's a lot of things which seem like mysteries. But, okay, the proof is in the pudding, and so something is happening. So let me try to explain what is going on. Okay, very good. So, big question number 2. I'll actually talk about 2 different versions of it, essentially, is what I'll call generalization. Why you actually do well when you're testing on x's you haven't seen with over-parameterization. So indeed, if you ever took a statistics course before 2015 or so, you were always told never fit the data. That was like you literally just get an F every time if you fit the data, right? So never fit the data. Okay, what do statisticians know anyway? Okay, I don't know. Actually, they know quite a bit. It's a little bit more complicated. So let me phrase the question this way. So I'll say it like this. So among a C, this is the infinite number of ways of fitting the training data of global minima. Minima of L. So Y does a local method, or whatever method you use in practice, GD, find good ones. That is, ones that actually fit the data and generalize to data you haven't seen. Right? Because if you just memorize the training data, that's not very exciting. Okay, so really there's 2 kinds of things to say. So let me give you 2 intuitions. So this is going to be intuition number 1. And this will come back to this linear thing, so it will hopefully satisfy Yvonne. But we'll see. You'll tell me. Yeah, we'll see. We'll see. So let me do a case that probably everyone who's taken a statistics course or a linear algebra course or whatever has seen in one form or another. Let me take a linear neural network. Okay, just one linear layer. So it's very simple. Literally linear in its parameters. I guess I called these f of xi squared. Okay, so this is the loss function that I have. This is my model. And okay, the key assumptions for me are that theta and xi are in Rn0. Okay, that's just my name for the input space. And that I have way more parameters than I have data points. Okay, that's the situation I told you that I'm in. So this is what I want to try to understand. Okay, so somebody already pointed this out. Okay, so here I am in Rn0. And okay, what am I doing? I'm just solving a system of linear equations, underdetermined system. So, if you don't if you remember your linear algebra class from whatever high school or undergrad or whenever one takes it, right? There's just a hyperplane of ways, I call it I for the space of interpolants, of fitting the data. So these are the thetas, so that xi dotted with theta is f of xi for all I. Okay, so you have this. So this, if you want, is my sea of global minima of the loss. There's infinitely many of them. I draw it like a line because I dare not draw in higher dimensions. Okay, and what do we know from our linear algebra days? We know that the data itself partitions this space into two natural directions. Okay, so there's the origin. So there's this direction. So this is the direction spanned by the x's that are in my training data set. Right? And these are the directions in which, if I change theta, I change the predictions on the x's that I have. And then there's the perpendicular directions. These are the kernels of the left-hand side, so to speak. So this is the span of xi perp. Okay, and there's a, if you look in a statistics textbook, or if you look at MATLAB or whatever you want, there's a special way of fitting the data, which without too much more information, people will typically tell you. I'll call it theta star to choose. So this is a way of fitting the training data with minimal L2 norm, okay, the thing that's closest to the origin. So this is somehow targeting this is why people regularize. Okay, if you're a little more sophisticated, you know about shrinkage, so maybe you don't want zero regularization. Doesn't matter. All right. So now what the heck am I doing? I want to explain to you why a local method, like gradient descent, can possibly find a good way of fitting the data. Okay, and notice this is kind of the difference between classical statistical learning theory and what I would call modern statistical learning theory. When you have an infinite kind of non-compact set of ways of minimizing your risk, you need to talk about the optimizer. The optimizer is what breaks the symmetry between choosing one minimum and another minimum. And so you have to analyze the two of them together. That's the difficulty of doing over-parameterized analysis. Okay, so let's make an observation. So NB, I'm going to write it here. I think this will be OK. So let me do something slightly embarrassing. And let me just calculate the gradient of the loss. Yes? Thank you. I'm a monster. Excuse me. Yes. Well, I'm a monster in many ways, but this one way I don't see sometimes. Yes. That's right. Okay, excellent. Excellent. Yes, listen to Yvonne, obviously. Okay, right. Indeed. Is this okay? Okay, so I want to explain how the optimizer comes into deciding which global minimum you find. That's kind of like the mystery. And, well, to understand the optimizer, you have to understand the gradients of the loss. That's what you use to update your parameters. So, okay, easy enough, right? This is 1 over n times the sum on I goes from 1 up to n of, you have your residuals, theta transpose xi minus f of xi. But crucially, times xi. Okay, so before giving away the punchline, because what's the fun in that? What's the point of this calculation? No, it's not to tell you that I know how to use the chain rule, which on a good day I do know how to use. What did we find out that was interesting? It's like hard to see that it's interesting because it's so simple.
It's a scalar product of those things. You make nice pictures.
No, but okay, there's only one object in my picture, which is the span of the xi's. What does the span of the xi's have to do with the gradient? Okay, I don't know who said that. Excellent. Okay, very good. So indeed, so here I claim this is the key observation. This belongs to the span of the xi's. And the reason this makes sense is gradient descent is greedy. It only moves you in directions that change the loss, right? It's always perpendicular to the level sets of the loss. But the loss only changes in these directions. So what do you learn from this? Well, you learn something very simple, right? If I had started over here with theta of 0, I actually can only move in directions that are parallel to the span of the xi's. And so optimization will simply move me in this direction and converge over here. So it'll be my theta of infinity. Okay, so what you learn is that the learned value of the parameters, theta of infinity, is just the orthogonal projection onto the space of interpolants of your starting point. Okay, so already you learned something very interesting. Okay, if you were worried about finding bad ways of fitting the data, you were basically worried about going off to infinity in L2 norm. That's like one thing you could worry about. And I'm telling you, your optimizer doesn't needlessly change the L2 norm of your data. Okay, it doesn't try to go off this way. It just goes as quickly as possible, because it's a greedy method, to the space of interpolants. Okay, so that's kind of cool, but let me kind of make this even more interesting. So suppose that theta of 0 was equal to 0. Okay, suppose I started my optimization at the origin. Okay, what's going to happen? What value of my parameters am I going to learn? Theta star. Okay, there's only one answer that's possible. You can only, okay, right. So indeed, right, theta star by definition is the projection of the origin onto the space of interpolants. It's the closest thing you have in the L2 sense. So if you start at 0, then theta of infinity is actually equal to theta star. Okay, so you see, it's a thing which is a bit weird at first. I never told you, at least you didn't think I told you, to regularize the L2 norm of your parameters. That's what a traditional thing would do, right? You add some ridge penalty and you're good. But actually, your optimizer had what's called implicit bias. Okay, this is what at least it's called these days, the implicit bias. It was because, okay, if you think about it for a little while, because my gradient that I chose here was L2 based, what you do is you minimize the L2 norm of the distance that you travel. That's the exact sense in which you're greedy. Okay, so your optimizer kind of baked into it some preference for simple ways of fitting the data versus difficult ways of fitting the data. Okay, and what I would say is the moral of this story is basically like this. So there's this whole field that studies the implicit bias of optimizers, that if you start near quote-unquote simple thetas, okay, in this context, so it's not always clear what simple means, but in this context, simple was starting near the origin, or at the origin. Okay, and you use a greedy method, like gradient descent, greedy optimizer. Okay, then what's going to happen is, of all the ways you can find to fit your training data, you're going to find the one that's closest to the simple place you started. So there's a kind of bias towards finding the simplest way of fitting the data. Okay, so then you find a fit to the data that's as close to their simple initialization as possible, the simple theta of 0 as possible. Okay, so this is just the moral. Okay, you have to be much more careful when you're, so here it was really easy because my model was linear in its parameters. And therefore, the gradient was linear in the things they were dotted with. And that was the driving kind of thing we used. When your model is an actual neural network, it's not linear in its parameters. And it's pretty clear that this is only part of the story for what's going on, for why neural networks learn a good way to fit the data. But I think this was kind of a big, I'll say, discovery. That somehow, like, you can encode in your optimization procedure directly a desire to find relatively simple ways of fitting the data. And this kind of, point of view also explains, at least to me, why it's so important to understand what happens at the start of training. So I'm somewhat obsessed with studying random neural networks, as Giovanni well knows. But one of the reasons to study random neural networks, i.e. neural networks when you just randomly initialize the parameters, is that where you start optimization has a big influence on where you end, precisely because there's so many ways of fitting the data. You're going to tend to end up relatively close to where you started. Okay, it's not a precise theorem, but that's the fact of life. And so, okay, so this is kind of the moral of this question number 1. So let me just pause and ask if there are questions or comments about this, because I want to get to the signal versus noise question, which you had raised before.
Well, isn't this contradicting what you showed us about the unique and minimum thing? I mean, it would seem that you're converting towards...
No, so you have to be careful. The unique minimum is as a function of the outputs. There's only one way of setting the outputs of the network to fit the data, but a statistician would say the parameters are not identifiable. There are many ways to get the same. So yeah, indeed. No, but that's the key distinction. That's right. You don't know which parameter vector you got. And so yes, I fit the data, but the question is how I extrapolate. Yeah, good. Other questions? Or? Yeah, please. So the reason I say implicit bias, sometimes it's called implicit regularization, is when you combine a nonlinear model with one of these greedy optimizers, it's not clear how to explain to a human what it's doing. Here I was able to draw a simple picture because everything was kind of linear. But it's not clear, is there some norm that you're implicitly minimizing in addition to fitting the data, norm of your function? Or is there some kind of shrinkage type thing that's going on, or sparsity thing, or whatever? And so I would say it's just an open question in general. Given a nonlinear model and one of these greedy local optimizers, what aspects of the model determine what kinds of fits to the data I find? So that's why I'm being a little vague, and that's why I think people are vague in general with the nomenclature. Does that answer the question? Okay, as well as I can. No, I mean, fair enough. But that's what one is supposed to do in the machine learning world, right? You just talk around it until it sounds good. Okay, I saw there's another question, yes.
Yeah, so I don't know too much about neural networks, but I kind of thought like when you start, you randomly initialize, and it doesn't really matter too much. But you now said exactly the opposite if I understood it correctly.
No, it matters a lot.
Yeah, so I didn't know that. So that should have a huge impact on how you work with neural networks.
Yes, it does.
I've not seen too much discussion about that.
So there is in fact a lot of discussion about it, but what I would say is that for relatively vanilla neural networks like this, it was worked out in a combination of theory and empirical guessing, how to initialize. And you don't hear much about it because if you don't initialize well, your neural networks, not only will you not learn a good fit to the data, typically you won't learn anything. You won't do better than random. It's just going to diverge. So you simply don't report it. Okay, it's not very honest, but that's how it works. And so yes, this question of how to initialize is very important. If you don't do it right. Yeah. Right. Okay. Lecture number 4 will be all about such. But it's yet another reason to analyze random neural networks. Because like in a sentence, the point is you would like to find a way of initializing your network so that the outputs and the gradients of your network are well behaved at the start of training. If they're not, you're not going to learn anything at all. And that's a question about some stochastic processes, blah, 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 depending on the setting. So yes, there's a lot of work on that. At least it's one of the things I'm excited about. Okay, I don't know what to say. But people in the real world care a lot. If they don't know how to initialize, they don't get anywhere. Yeah, for sure. Yeah.
Is there any mathematical result that tells you that if you have more parameters than data,
yes,
that neural network with a nonlinear activation function will be better than just a linear model? And in which sense?
Yes, so the short answer is there are results of this form. So there are results that, there's two kinds of results. There's essentially sample complexity results, which say any linear model takes at least so many samples to learn a certain class of functions, but your neural network can learn it with much lower sample complexity. That's one kind of result that exists. Another kind of result that exists is you can show that neural networks, in some cases, correspond to data-dependent kernel methods. And so what you basically find is you find that they implicitly learn kernels that align with your data generating process. And then you apply standard learning theory to say that such things generalize better. So I don't know if you want to think of it as a generalization or sample complexity kind of guarantee. But there are theorems of these two kinds. I would say there's order like 10 such theorems. And so not very many relative to the number of theorems that are out there. But yes. Okay. Other questions or comments? Yes, please.
This kind of blessing of overparameterization is related to there are some paper that claim that adding pure noise in the data kind of improve like the predicting power of related.
So it is related in the sense that there are people who study the question of, imagine you take kind of vanilla gradient descent, but you add noise to it in various ways. You could then ask, what are you going to find? Or relative to what you were going to find before, what are you going to find now? And the kind of theorems you can prove are what you're going to find is going to be different in some more or less precise sense. And then depending on your data generating process, it might be better or worse. I mean, there's kind of no free lunch. But you can see the differences coming out, and you can kind of see them on this picture. You know, one optimizer is going to go this way, some other optimizer is going to go the other way, and what was better kind of depended on your data. Yeah. Great. So let me get to the signal versus noise stuff. Okay, I have lots of time. That's not quite true, but I have some time. Okay, so this was story number 1 about why overparameterization is okay. But somebody asked me, and I think it's a very sensible question that people have studied now quite a bit. And it's interesting even for linear models, believe it or not. Okay, so somebody asked, what if you have noise? Okay, one of the basic maxims in any statistics textbook, as I said, this oldish statistics textbook, is don't fit the noise. So let me see, I wanted to write it down. Too many pieces of paper. Okay, excellent. So here's version number 2 of this overparameterized question. Okay, so let me make it very concrete. So suppose that your data generating process, f of xi, was some true f of x plus noise. Okay, it doesn't really matter, but I'll just write it in case people are on their phone and they can look up and see what I mean. Let's say Gaussian noise. So in practice, the thing you do, regardless of whether you think your data is noisy, is you basically exactly fit the data. That's just how it is. And so the question is, why is it okay to fit the signal and the noise? Okay, so I apologize to people who know statistics quite well, but let me just kind of caricature this. Okay, so let's imagine, so here's the inputs are, and let's imagine that you have 3 data points that you've observed. Okay, 1, 2, 3. And let's imagine that the true data generating process was f star as a constant, let's say equal to 1. Doesn't matter. Okay, that's like, so just to make a cartoon of what's going on, I want to try to explain why overparameterization is not always going to be bad for you, but let me show you the typical picture for why overparameterization might be bad for you. Okay, so let's just imagine fitting these 3 data points with polynomials. Okay, so it's not a neural network, but it doesn't matter. It's the same idea. So if you have a degree 0 polynomial, okay, maybe you learn this. Great, so that looks not too bad. If you have a degree 1 polynomial, maybe you look this. Also, not terribly bad. Okay, there's a unique degree 2 polynomial that passes through the data. So this starts to look scary. Okay, and then obviously there's infinitely many degree 3 and higher polynomials that go through the data. So the question is basically, why am I not learning this one? So this is, let's say, degree 20. Right, it passes through my data points, and it's obviously a terrifying thing to do in practice. Okay, and this is what I mean, for people who don't necessarily use these words, by fitting the signal and noise. If you go exactly through the data points, you just force yourself to oscillate, seemingly, if you don't have much noise. Oh, sorry, if you have some noise in the data. I said exactly the opposite thing. Okay, so here's my claim, which is very poorly understood. Although there are some theorems and there are some predictions. So this is sometimes called benign overfitting. So the observation is that neural networks fit the data, at least often, fit the data exactly and generalize. Okay, so here's my question to you. How is this even possible? I don't mean to prove a theorem, but can you, is there any interesting, truly degree 20 polynomial or high degree polynomial that passes through the data and actually does a reasonable job of predicting the constant function? Forget about polynomials. Any reasonable kind of wiggly function.
Well, if you find a solution which turns off all the high order terms.
Well, so then at best you'll get the degree 2 fit. Yeah. That's still very sensitive to the data, right? So you're right, but that's actually not the answer. That is a way to try to do it. Right, so you'll get the degree 2 fit to the data. But I mean, for general, like, with probability 1 over the noise, whatever, I don't know, some kind of, okay. No, so no, that's not quite the right thing. I claim something much more dramatic is happening. Okay. So what picture should I draw? Like, I want to know what the neural network prediction should look like. That both fits the data and generalizes very well.
Maybe the kind of the bad stuff is outside of where you want to generalize.
Okay, that's possible, but okay. So at least for the theorems I know, for linear models, the bad stuff is right where you want to generalize. No? Okay, so this is where you have to suspend disbelief. Here's an example of a function. It's the constant I want, and it just has these little blips. Hey, what's wrong with that function? That fits my data. It generalizes well. Okay, so here's the point. Yeah. Okay, excellent. In the L2 sense. You see, if the places you don't generalize are very close to the training data points you have, then who cares? If you just select a random data point, you're going to be basically where you're supposed to be. So here's the point. This is kind of like some theorems / conjectures / whatever. But they're exact theorems about this happening for linear models in high dimensions. So neural networks and high dimensional linear models use the low frequencies to fit the signal. And high frequencies. Using high frequency is basically what allows you to be highly localized to fit the noise. Okay, and therefore, if you believe this, you get generalization, say in L2, but you don't, but not in L infinity, for instance, or for LP for P high enough. Okay, so this kind of brings me to one of the points I wanted to make, which is one of the fascinating things about neural networks. Every neural network maybe you've heard about these things, is the existence of adversarial examples. Okay, just out of curiosity, who's heard about adversarial examples? Okay, some people have and some people haven't. So here's the point. Every neural network you've ever used in your life basically has the following property. You give me any input you want that's correctly classified or incorrectly classified, doesn't matter. I can find basically an infinitesimal perturbation of it, which to you won't seem any different, but which can be classified any which way I want. Okay, like an airplane becomes a fire hydrant. The famous picture is pigs fly. The pig becomes an airplane, whatever. So these are called adversarial perturbations. You have to search carefully for them, but basically in a very, very small neighborhood of the inputs. You can always find something where you misclassify. And I think a kernel of the reason for why is something like this. If you have this function that has these very small support but big magnitude spikes, and if you believe this kind of happens in every direction, everywhere in high dimensional spaces, then indeed there should be these directions where you very rapidly change the function value. Okay, that's just a kind of conjecture, but the fact that these adversarial examples exist is a fact. And we don't, in fact, even know, are they necessarily there? Is there just a theorem? There's no such theorem that I know of that would say if you do learning in high dimensions and you can learn it and you can do learning efficiently, you automatically have to have adversarial examples. That would be a beautiful theorem to prove. Or no, people have spent hundreds of millions, probably billions of dollars at this point, trying to find ways of tweaking your optimization algorithm to make it so that you both fit the training data and don't have adversarial examples. And I guarantee you, anything you can think of immediately to try to do, someone has tried, and it failed. Okay? Though, okay, maybe not, with probability 93%. Okay? Maybe you're...
So just a quick comment.
Yes?
The last statement for statistician would just mean, okay, typical destination for such a model is, okay, I take any L2 expansion of F star, I truncate according to smoothness of a star, and I estimate so and so many coefficients. So when I truncate, I consider only low frequencies. It gives me the signal. And the one thing as a statistician which I typically ignore in my estimation, that's the norm.
Yes, and somehow the effect is in high dimensions. It's okay to not ignore the noise if you have many directions over which you can spread it. You know, somehow that's supposed to be the geometric like principle. Like your noise is kind of like doesn't know about the directions you're trying to learn, and so it's okay to fit the noise because the predictions you're going to try to make are going to be close to orthogonal to noise. Your prediction for the noise is going to be spread out over many small eigenvalue eigenvectors, and that's supposed to be okay. And okay, there are papers on benign overfitting. Benign. I don't think I spelled it right. I'm a failure. Okay, benign overfitting. There we go. Which prove this and give you the ways in which it works and so on for linear models. But like, okay, there's some hope that for neural networks that's the way it works in general, but we're not sure. Yeah.
I just wanted to because of the figure, as you said before, that the Arsenal parameters is a good thing. But if we look at this figure right now, we said the exact solution is basically the exact function we agreed to. Then the neural network gives me a horrible fit.
Yeah, so indeed, it's so what I'm saying is when I say something works in practice, what I'm saying is for the kinds of data sets people train on, the kinds of functions that your neural network is biased towards seem to be good. For sure, you can, from your training data, if you have no regularity assumptions on the function at all, you can do anything. There's no generalization guarantees possible without like some kind of hypothesis on your model class. That's a fact. And so, yeah, but just, why are we hoping to try to learn the degree 20 thing, or the degree 2 thing, or whatever? Yeah. So the mathematician has to find plausible assumptions on the data and provable results on the optimization that marries the two. That's kind of the dream theorem in a sense, and they're mainly missing. No, there's some progress. Yeah. Yes, please.
What does high and low frequency mean?
Okay, if you know about wavelets, for example, maybe that's the best analogy I can tell you. Like high frequency means you can wiggle a lot. That's the usual like cosine of 100x. That's what I mean by high frequency. Cosine of x doesn't wiggle very much. And so but I mean, not only can you wiggle a lot, but you can be localized. Like you can go up and down in a very short span. That's kind of what I mean by high frequency. Okay, so that's the kind of thing you need to make this kind of bump. If I told you I had a degree 2 polynomial, it can't do this kind of localized fluctuation. There's some kind of like... But the way you should think about it is, when you're training your neural network, you can learn the coefficients at various frequencies. And so it's just a question of how much of a given frequency to use. Yeah, so they have low amplitudes, but they can be very highly kind of localized, and it's just a picture, right? I mean, like I don't have a theorem about this for neural networks. Yeah, all I can do is draw this on the board. Okay, so there's one more thing I wanted to say, and let me say it, but it's short because I have very little to say. But I think it's a beautiful question, so unfortunately I'm going to erase the website. I'm sorry, Giovanni. I tried to save it, but it died. The patient did not survive. Okay, so here's kind of question number 3, and then I'm going to stop. So this is what I'll call feature/transfer learning. All right. So let's make the following observation. So the output of a neural network looks like this. So if I take the ith component of the output, I'm sorry, it's a kind of debauch of indices, but it's just the way it works. Right, so this is the ith component at the output layer, at the input x, with my setting of parameters theta. It's just how it is. If I were to write it, it looks like this. Right, there's a bias, and then a sum on, let's say, k goes from 1 up to the hidden layer width of the previous layer of my weights, WL, I, k. And then, let me write it this way, there's some function phi k of x and theta, where, of course, this phi k of x and theta is nothing more than sigma applied to zl k of x and theta. That's just the definition of the output of the neural network. I'm just trying to emphasize that the output of a neural network looks like it's a linear function of its parameters, and it is a linear function of the parameters in the final layer, but then it has basis functions, these phi k's, which themselves are parametrized. That's one way of thinking about it. Okay, so what you're supposed to kind of take from this picture is the following kind of simple fact. Let me see, I have some clever way of saying it, or not really. No, I rarely have clever ways of saying things. Okay, fine. So I'm going to write it this way. Okay, so neural networks learn, when you train them, both the coefficients, these w's, and let's say this b as well, and the basis functions at the same time. Okay, so if somebody is to ask you, what's the difference between machine learning a la 1960 and machine learning in today's world, the answer in some sense is trivial. Back in the day, what somebody would do is somebody would give you a collection of linear function, or sorry, of functions, these basis functions, phi k. Someone hands you that, and what you do is you try to learn a bunch of coefficients. You try to learn the coefficients in a linear combination of these functions to model your unknown function f. That's what a linear model does. That's what a kernel method does, and so on. But neural networks are nonlinear, and more precisely what happens is they learn the basis functions and adapt them to the data that they see. Okay, that's like, in a sense, the difference between neural networks and linear models. And the basic question is the following. So what aspects, okay, or maybe statistics, if you want to put it this way, of your data generating process F are learned, or maybe encoded, in the basis functions phi k? In what order, do you learn something about your data generating process first during training, and so on? Okay, so when people talk about neural networks, they usually talk about, oh my god, they're amazing at learning features. And at least one version of exactly what they mean mathematically is that after you train a neural network, you learn this beautiful data-dependent set of basis functions that you can use. They're somehow adapted to the data that you have. And it would be nice to have a concrete description of what kinds of functions you learn as a function of the training data, okay, and the algorithm and the model. You have to put it all together. And so just to come back to ChatGPT or any of these kind of large neural networks, one of the ways people use neural networks in practice is you first take a huge data set, like all the text on the internet. Can you train a gigantic neural network to predict the next word or the next token in such a data set? And from this, you roughly speaking learn the b's and these w's and these phi's. Then what you do is you throw away the b's and the w's, and you reuse these basis functions phi k for new tasks. So now somebody comes to me and they're a hospital and they want to predict the next word in a medical document. So they have a much smaller data set, but the model that I currently have doesn't do a good job. It's trained on all possible data. So what you do is you basically train a new collection of these outer b's and w's using the same basis functions, or maybe you keep training the thetas and the basis functions sometimes as well, and that's called fine-tuning. Okay, so that's what feature learning, feature transfer really is all about. That's like kind of the transfer learning paradigm. You do pre-training on a big data set, and then fine-tuning or a little bit of extra training on a downstream data set for which you have less data. And that's typically the best way we know how to make good models for data sets in practice. And so this kind of question of what statistics you learned in your original data set really becomes important, because you seem to learn something that's useful, not just for the task you started with, but for other tasks. Okay, and it's unclear how to make theorems about that, but it's something that I'm thinking about quite a bit, and I think it is possible to make progress, and okay, other people make progress as well. Yeah, please.
So I have a question, these phi's, do they agree it's something that was already in your original definition, or is it something new?
So I'm just saying that it's just in my original definition. I'm just saying the kth basis function is just what the kth neuron in the final hidden layer calculates. This is just a definition. If you were to put the sigmas in here, that's all that it is. I'm just writing it in this way to emphasize that you're learning a bunch of data-dependent basis functions.
But you also said this is kind of new and opposed to the old, but like they had many many layered neural networks already 50 years ago, so I don't quite understand.
No, sure. So all I mean, in a sense, is that if you ask what's the difference between a neural network and a linear model, linear models in my mind are completely understood in the sense that we know every linear model has a Hilbert space associated to it. Every question about the linear model is about some spectrum of some operator on this Hilbert space. Maybe I can't compute the spectrum exactly for a given operator, but I can tell you at a high level what matches to what. And the difficulty is somehow that the nonlinearity gets baked into the fact that I'm searching over the Hilbert spaces as well, if you want to put it that way. And it would be nice to have an answer to what kind of Hilbert space I learn as a function of the data. That's kind of what I mean. So people have been using these kind of multi-layered neural networks for a long time, but we still don't understand what they're doing. And so it's like so these days it's even a more important question than it used to be, I would say. Yeah. Okay. Yes.
Can you make any statements regarding this point with respect to the layer? Like the final one has, I don't know, better progressive properties than one before, and so on. You choose to train a new model.
The truth is that I don't know of any such theorems. In practice, people try a million bajillion things, and sometimes it's better, and sometimes it's not, and you know what I mean.
Just because of your example, for example, with the hospital, you said, well, you could take, so to say, the basis functions that you found from the last layer.
Yes.
Do you have any guarantee that will give you better results than taking the ones from one layer previously?
No, absolutely not. But you don't know what else to do, so you do it. You know, that's just how it is. Yes, please.
I'm just trying to understand this. Instead of using the language of approximation theory, you use the language of statistics.
Yes.
So is it fair to then call a neural network an estimator of the model that you have written down in your loss function? So is it fair to say that what is the model that the neural network is estimating? It is the f that you have written down in your loss function, right? Is it fair to say that?
So yes, with the asterisk that again, your parameters are not identifiable. But you don't care about the parameters, you care about the predictions. Like the function you're estimating is, of course, identifiable. I mean, it returns a concrete output for any input. And so yeah, what I would say is yes, neural networks are an estimator for this kind of function. Like this really is, I just, how to say it? They're non-parametric like you're just doing non-parametric regression in this example. That's the most kind of general thing, and it would be nice to constrain that a bit more, but it's not 100% clear what to connect it to for me.
Non-parametric regression estimation.
Yes.
Then can you do the distribution? Is there a distribution theory available for?
So that would be the dream, and the short answer is no, but the slightly long answer is sometimes. Okay, so no in the sense that even at the start of training, it's not so easy to understand the distribution you begin with, let alone what happens after you train on your data. Okay, so in general, there's basically no theorem, except for the one I'll present in tomorrow's lecture, which tells you anything about the distribution of predictions after training. We just don't have such a thing. Okay, but if you, instead of doing optimization by gradient descent, you want to do learning by Bayesian inference, who says you can't do that? Instead of thinking about optimization by gradient descent, you think of the initialization as a prior over your parameters. You compute the predictive posterior, and you ask what happens. Then in some cases, we can write down more or less concretely what's going on. And you can get some kind of distributions and guarantees and so on.
So for example, if you did that non-parametric regression of y and x, you can compute it, you can figure out its limiting distribution under. Why can't you do the same here? So what is the difficulty in figuring out?
The difficulty is analyzing the learning algorithm.
There is no statistical model here, first of all.
No, but you could put in a statistical model. You could just say, imagine your x's are sampled IID from something, and you have some distribution of. No, but I'm saying even given such a model, the issue is we just don't know how to explain how to get your hands on the statistics of what happens after learning.
But this is an extreme of estimator, right? In the end, you're solving an optimization problem. The outcome would be the neural network.
No, but because you're over-parameterized, it's not enough. There are many ways of fitting your neural network to the data, which give terrible predictions. But your optimization procedure happens to choose a way that doesn't. And so you have to analyze, if you want to put it formally, you start with a probability distribution over functions before training. Then your optimization procedure is like a push forward of this probability distribution onto the space of ways of fitting the data. And you have to describe to me the statistics of that push forward measure. And presumably, okay, in practice, it's concentrated around some kind of nice ways of fitting the data, but we don't know how to make that precise. And so it's not extremal because it's like an underdetermined problem. So like, okay, I erased it unfortunately, but if you think back to the linear model example, if all I told you is that you fit an underdetermined system of linear equations, you can get no guarantees for such a thing because you could have had arbitrarily bad fits. But it's your optimization procedure that told you which of the fits you chose. And so you somehow have to be able to figure out what fit you actually got to the data.
If your f was a very nice identified, so if the parameters in the f function were identified in the standard sense,
yes,
would the neural network estimator coincide with like a standard optimization?
So yes and no. So here's the trouble. Either you believe that you're correctly specified and your f is generated by the same architecture with which you're trying to learn it, so then you will never learn it in practice. Optimization will be too hard in high dimensions. You won't actually be able to learn the setting of the parameters that generated your f. That's just...
So neural network cannot solve nice?
No, indeed. It needs to be very over-parameterized to make optimization tractable, and then you're just by definition misspecified. Just think of them as some kind of Gaussian process type of thing. And then, okay, just because I conditioned my Gaussian process at some points to take some values, if you didn't tell me anything about the regularity of the process, there's no hope. Could have been a white noise process, and you have no generalization. So you just need more information on the optimization itself. That's kind of, yeah. So you give up any kind of identifiability of your model. And that's the price you pay. It's harder to figure out what you learn. But it's easier numerically to actually learn something. Yeah. Yes?
Why even nonlinearity is just one real function or action?
The short answer is because people have tried doing more difficult things, like more computationally intensive or interesting things, and it doesn't seem to lead to better performance. That's not to say that tomorrow you can't find a clever way to use a more complicated nonlinearity and do much better. But it seems to be unnecessary. That's there's no principled answer that I know of to that question, yeah.
But also the answer like in the approximation theory itself, like which class of functions you can approximate, and then it says it's enough to take this class.
So I actually don't believe that, in the sense that I think approximation theory tells you almost nothing about what you will learn. The neural networks are so large, you can approximate any function to your heart's content, with any architecture you use, whatever. And somehow some architectures will do well and others won't, and it's about which functions you can learn.
Yeah, well, I'm just answering.
Oh.
That it's sufficient. I mean, from approximation theory.
Okay, that's...
It's sufficient.
But you could imagine that if you made a slightly more complicated nonlinearity, you could be way more parameter efficient, for example. Right? So, and the answer is you probably could. And we haven't seemed to be able to find a way to actually make that do something good in practice. But it's conceivable that it's possible. It's just no one has done it to my knowledge. Yeah. Okay, I'm of course lying a little bit. This is not the only kind of neural network that's out there. Like transformers have much more complicated nonlinearities. They have these self-attention things. And so in some sense, there are more, but it's not clear that that's fundamental. That's kind of what I would say. It can give somewhat better performance, but the basic phenomena kind of don't seem to need very complicated neural networks to make happen. Yeah. Yes.
So what you are claiming is that with this type of simpler model, deliver probably something possible?
So the short answer is, okay, in two parts. Transformers were originally invented to use the hardware that we have, the TPUs that kind of Google uses, as efficiently as possible. And some people believe that the main use of transformers is just that they're hardware efficient. And to try to validate this point, there's a recent paper, relatively recent, out of DeepMind, where they went back to what are called recurrent neural networks, which are used to be used for sequence modeling. And they basically just scaled them up to the same scale as the modern transformers. And they found that they got comparable performance on these kind of language tasks. They didn't beat the transformers, but they got pretty much the same performance. And so it doesn't seem to be that it has to be a transformer. Now, the transformer could be more useful in practice in ways we don't fully understand. Lots of people are trying to understand learning with transformers. But it seems like as a thought exercise, the transformer is not fundamental as far as we know. Yeah.
I want to ask you again, why is it called feature or transfer? I mean, what do the words feature and transfer have to do with the mathematical formula?
Okay, so you know when you have a kernel method, underlying every kernel is a feature map. And so quite literally, you can think of these as the elements of your feature map. You know, if you were to just train the W's, the kernel you get is the inner product of these feature maps. So that's where the word feature comes from. And so people kind of use it. But it also, like a lot of things in machine learning, you use words that sound nice. Feature learning is more interesting than basis pursuit. You know, basis pursuit sounds like maybe you're playing baseball or something like that, right? Say, oh, you're doing feature learning. Okay, so transfer learning is this idea that you can learn features or kind of train a neural network on one task, and then transfer those features to another task. So that's the paradigm people will kind of call it as transfer learning. You train a big model on a big data set, and then you fine tune it. You do a little bit of training on a downstream data set, and that's the transfer from one task to another. That's just the word that they use to kind of be evocative, I think. Yeah.
Even the parameters of the model are not identifiable anymore. If you just assume that you get an estimate, let's say f hat from your neural nets, and you look at the L2 distance between f hat of x and f of x, do you have something like a consistency result?
The short answer is no. I mean, again, the trouble is it's very hard to actually analyze optimization with nonlinear models. And so it's just, you have to have some kind of control on the f hat that you get. And the kind of picture that I drew is meant to be indicative of the fact that your f hats, if all you know is that they fit the data, could be arbitrarily far from f. In the sense that like, they could go off to infinity in your function space. And so, yeah, a lot of work has gone into and very little progress has been made, although some has been made. And I'll present some of that in the next 2 lectures on like actually getting your hands on f hat. Like what's its regularity? You know, that's like one way of phrasing the question, right? If I told you that f hat fits the data and is Lipschitz, or and is whatever, you know, Holder or something, okay, then I can start saying something about how to extrapolate. But like, it's hard to do that. Yeah. I don't have a better answer, unfortunately. Okay, I've exhausted the audience. Excellent. You know?